This is section 1.3, part 2. So we've studied several strategies for finding limits for lots of different kinds of functions, that the ones at least that can be done by direct substitution. All of that knowledge, along with Theorem 1.7, can be used to develop a strategy for finding limits. Let C be a real number and let f of x equal g of x for all x not equal to c. We had a function, I think it was an earlier recording, and it looked something like, let's see if I can remember it, x cubed minus 1 over x minus 1. And we factored that to be this. And we said that, and I didn't say it this way, but basically I said if there's a g of x that is x squared plus x plus 1, f of x and g of x are the same thing, except at one point when x is 1. Then they're not equal, because f of x is undefined and g of x is equal to 3, I believe. So seems to me I remember 4, but it may have been what I said before, and that would have been wrong. So if I said that was 4, I was mistaken. That would be 3. So I have to go back and look at that one and see if I messed that up. But anyway, these functions will have the exact same graph, except at the one point where x is 1. F will have a removable discontinuity. I can't remember if removable has an e in it. Is it that or without the e? Let me write both of them to see which one looks better. I used to be a pretty good speller until I learned German, and then my spelling went awry. Oh well, whichever one of those is correct. We'd have a removable discontinuity, at x equals 1. And the way I might say that is removable discontinuity. That's the way I'll get away with not knowing how to spell some things. At x equals 1. Well, if you'll remember, we saw this earlier. A removable discontinuity is a place where there's just a missing value for a given x, and it's just a hole in the graph. And so typically what we do is we want to find this function that's equal to it for everywhere except for at that particular value that's no good for f, and calculate g of 1. I really hope I didn't accidentally say that was 4 earlier. Wow, that would have been bad. And so what we'll say is, now that we know what the y value is for the g function when x is 1, it's actually more proper to say the removable discontinuity as at the point 1, 3. So that would be the coordinates of a particular point where there's an open circle. So when you have a removable discontinuity, it's proper to say the coordinates of the point where that hole is located. Okay, so what we can use this for is if f of x and g of x agree, except maybe at one point, like maybe x can't be c. Up here we can't let x be 1 in our example. Then the limit for f of x as x approaches c and the limit for g of x as x approaches c are the same thing. So if this is one function and that's the other one, they look the same except for this one actually has a dot there, then the limit for this one, say this is C and that's L, and let's say this is C and that's L, they have the same limit, L, if there's a removable discontinuity there. So if they agree at every point but that one, remember the limit only works on what is it approaching as a y value, not necessarily what it is at that place. So it's approaching L, just like this one is approaching L. The one on bottom happens to have a value there, which means direct substitution would find it, but the other one doesn't, and so we're going to have to find another way to do that, like rewriting our function in a simpler form using algebraic things like I just did factoring and canceling to get an equivalent expression for f of x to be g of x equals that quadratic trinomial x squared plus x plus 1. Okay, so now let's look at example 6. Oh, I'm sorry, that's basically what we just did. Oh, I take it back. Well, we sort of did it. So the question is, what is the limit as x approaches 1 of x cubed minus 1 over x minus 1? And so when you try substitution, you'll get 0 divided by 0. So that's not a number, so we cannot do direct substitution. So then we have to back off and try something different. And one of those different things to try is try factoring and canceling, which happens to work in this particular case quite nicely. Because doing that canceling doesn't change the function except for at 1. It's taking away the fact that we would be dividing by 0. So after canceling, you get this, and this one can be evaluated using substitution. You can see how I felt like we kind of talked our way through this one already. We just hadn't applied the limit idea to it. Okay, so that is what will happen if you substitute and get 0 over 0. This is one of our tricks, is see if factoring and canceling will work. So here's a page of strategies for finding limits. Number 1, learn to recognize which limits can be evaluated by direct substitution. These are all listed in theorems 1.1 through 1.6. When the limit of f of x as x approaches c cannot be evaluated by direct substitution, that is usually because you're trying to divide by 0, try to find a function g that agrees with f for all other x values other than x is c, like factoring and canceling. Then apply theorem 1.7 to conclude analytically that the limit as x approaches f of x will be the same as the limit as x approaches c of your g of x, which agrees with f of x except for its c, and that'll be substitutable and get g of c as your answer. You can always use a table or a graph to help reinforce your conclusion. That is not an analytic answer just to have a graph or just to have a table. That's more like confirmation of your answer more than anything else. This factoring and canceling that I've been referring to, this book calls it the dividing out technique. I guess that's okay. So here we go. Let's do a limit. And I'm going to say basically always try substitution first. In every limit question, that's your go-to. So don't forget that when we've done a lot of different things and I come along and give you one where you can just substitute and get an answer, and you're sitting there trying to figure out, well, should I do this technique? Should I do that one? Please don't do that. Try substitution first. So if we substituted negative 3 in, we would get 9 plus negative 3 is 6, minus 6 is 0. And then negative 3 plus 3 is 0. 0 over 0. That's actually called an indeterminate form. We'll come back to that idea at another time again. I know we talk about it in this class later, and I know I talk about it in Calculus 2 as well. So that's a thing that we're going to have to live with and learn how to deal with. And for right now, our strategy is, hopefully, we'll be able to factor and cancel. So let's see if x squared plus x minus 6 factors. Yep, the x plus 3 and x minus 2 are its factors. Again, if you need to review factoring techniques, please make sure you do so. It's to your benefit to make sure you can do this. Otherwise, it's going to be really hard for you to find the answer analytically and show me work that leads to the correct answer. So here the x plus 3's cancel, leaving x minus 2. And now try substitution again and see if you can do that. And you can. And you get an answer of negative 5. Okay. So that is a really good technique. And if you graph this function, you see that it's a line with a missing point at negative 3, negative 5. It's a removable discontinuity there. So it makes sense that if that's what's going on, that as x is approaching negative 3 from below, negative 3 and from above negative 3, that this is approaching a y value of negative 5. So that's kind of graphical confirmation of what we just found. Okay, so again, that 0 divided by 0 is called an indeterminate form because we can't determine its value simply because it's 0 over 0. We can't figure it out from that fact. Sometimes 0 over 0 is going to give us an answer like negative 5. It could be 7, it could be 216, it could be pi, who knows what it could be. It could be anything. So it's indeterminate just from the form alone. So when you encounter this form, we'll have to rewrite the fraction so that the new denominator does not have 0 as its limit. So notice when we've canceled that x plus 3, the denominator is technically division by 1. And when you put negative 3 in for each x in the constant 1, you'll get back 1. The limit of the constant is the constant, and that's not 0. So factoring and canceling is a good technique. Another technique involves rationalizing either the numerator or denominator. Now, I know that, I'm going to review this a bit. I know that you know when you have a radical that looks like this in pre-calculus, you dutifully learned that we can't have radicals in the denominator. So you learned to multiply by a form of 1, like in this case, square root of 5 over square root of 5, which is 3 square roots of 5 over the square root of 25. And I'm probably putting more steps than a lot of you need, which is 3 square roots of 5 over 5. And now the denominator is not an irrational number, it's a rational number, like 5. Okay, then going back to algebra, you got to think about this a little bit harder. If you had, for example, 2 over the square root of 3 plus 5, to rationalize that one, because it's a binomial, the form of 1 you chose was different. It was not square root of 3 over square root of 3, because that 5 square roots of 3 would still have that radical. What you do instead is you multiply by 1 in the form of the conjugate of that binomial. If you recall, the conjugate of a binomial is the same numbers with a different sign in the middle. So the conjugate of a plus b is a minus b. The conjugate of a minus b is a plus b. Okay, so when you multiply by the conjugate, you need to realize that, let me remind you of something, when you multiply conjugates, may think of using FOIL for this. You should get a squared minus b squared, a difference of two squares, because the negative ab and the positive ab, the outer and inner products, add up to be 0. So that's a good thing because that allows us to get rid of square root radicals if we're squaring them. So in the numerator, this will be 2 times the square root of 3 minus 5. Notice I'm not distributing yet in case something reduces below. So this will be the square root of 3 squared, which is 3, minus the square root of 5 squared, which is 5. 3 minus 5, of course, is negative 2. 2 and negative 2 cancel, leaving a negative 1. And then if you distribute, you get negative square root of 3 plus 5. Or you might want to write it as 5 minus square root of 3. Okay, so that's how you rationalize square root radicals that are in a binomial. So that's going to be used here. Let's look at this problem. The limit as x approaches 0 of the square root of x plus 1 minus 1 over x. So let's try substitution first. 0 plus 1 is 1, the square root of 1 is 1, 1 minus 1 is 0, and substitution gives you 0 in the denominator. So this one cannot be done by substitution. And even though in prior to now kind of class, you would not have ever tried to rationalize the numerator. That's what we're going to do here. It doesn't have to be the denominator that's being rationalized. So we're rationalizing. And the binomial that we have will have a conjugate of square root of x plus 1 plus 1. And of course, we're multiplying by a form of 1, so the denominator entry has to be the same thing. Okie dokie. Another thing I haven't really mentioned yet, but I probably should. I'm going to go back because it came to me. Like, look at this problem. I kept writing the limit as x approaches negative 3 until I actually did the substitution of negative 3 in for x. So that's part of the problem as you go. Until you actually do the substitution, you keep writing limit. I did that up here too. I didn't take away writing limit until I actually put 1 in for the value of 1 in for each x. So kind of keep that in mind so that you don't accidentally lose some points. All right, so the conjugate will give me, or conjugate multiplication will give me a difference of 2 squares. So the square of the radical x plus 1 gives me x plus 1 minus the square of 1 is 1 over x times the square root of x plus 1 plus 1. Okay, and I'm not distributing that x on purpose because that's the thing that's making me divide by 0, and I want that to go away. So I don't want to lose it by distributing it through. X plus 1 minus 1 is x. And now you see that that x in the numerator cancels that pesky x in the denominator that was making me divide by 0. And so after we've canceled those x's, we're left with 1 divided by the square root of x plus 1 plus 1. And now try substitution. Notice I'm not writing limit now because I'm doing the substitution of 0 in for each x. And when you simplify that, you get 1/2. And again, you could, if you wanted to, make a table of values for this function as x gets closer and closer to 0 from both the left side and right side. Or you could look at a graph of this function and look at what's happening on the left side and right side of 0. And it should be approaching the y value of 1/2. So the next theorem that we're going to use concerns the inability to find a limit for some functions. And so what we have to resort to is a theorem called the squeeze theorem. Let me present what that is. Let's say that there's some function f whose limit we're trying to find as x approaches c. But that is a function that, try as we might, we can't figure it out by substitution. We can't factor and cancel. We can't rationalize. There's nothing in our bag of tricks that's going to work. And so we know that there's a pair of functions that we know a whole lot about, and we can evaluate their limits as x approaches c quite well. So here's another function, and what you know is that this function, let's call it g, is always greater than or equal to f. Okay? And then let's say there's another function, this one, we'll call it h. And the thing that we know about h relative to f is that f is always greater than or equal to h. So putting these two ideas together means that h of x is always less than or equal to f of x, which is always less than or equal to g of x. And our supposition here is that both h and g are well behaved. We know all about them, and we know how to deal with them and find their limits. So we know that as x approaches c, the function h of x approaches some limit L. And we also know for another well-behaved function, the g function, that as x approaches c for the g of x function, we also can find it using techniques we already know, and it also is L. And because f of x is squeezed between h and g, it's always between them or equal to one of them. And we also know that the limit for the upper function is L and the lower function is L, which it means that the function f of x has to be also going to L, and because it's squeezed in between. So we can conclude, therefore, that the limit as x approaches c of f of x that's between h and g has to go to the same thing that the other two are forcing it into, L. So there may be a function you don't know how to do its limit, but if you can find a greater function and a lesser function that as x approaches c go to the same thing, then that will force your function in the middle to go to that same thing. This is called the squeeze theorem. Okay. Oh, and by the way, I don't know if I've said this before, but those three dots I use is a mathematical way of saying therefore. It's a kind of a conclusion that we sometimes will want in math to say, oh, and by the way, here it is, here's the big finale, the conclusion is, and we'll put those three dots to say, here it is, we're done. Hip hip hooray. All right. So some people call the squeeze theorem the sandwich theorem, which is what I learned when I first learned this. And some people call it the pinching theorem, which I had never used before, but that's okay. There are all kinds of names for these things. Now, if you look at theorem 1.9, there are a couple of limits that I'm going to present to you without proof. I'm just going to say you need to know these, memorize them, whatever it takes to know these two specific ones, because they're useful when doing proofs, and you'd have to know that they're true. And we'll prove them later. But the limit as x approaches 0 of sine of x over x, if you'll look at the graph of that, I hope that you're convinced, graphically at least, that it approaches 1, or look at it numerically. As x approaches 0 from the left side and the right side, the values are approaching 1. And then another one that I'd like for you to know, again, I'm not going to tell you why it's true. I just want you to memorize it for now. And later we'll learn how to do it in a much easier fashion than memorization. But for right now, please memorize them. So 1 minus cosine x over x, the limit of that function as x approaches 0 is 0. And again, you can look at that numerically or graphically to see that that's true. Okay. Part of the reason we need those is because in one of the proofs that could be done here, the squeeze theorem is used, and we're going to need to know those particular answers so that we can squeeze some things between. All right, so anyway, how might you use these for right now? Because I'm not going to have you do that proof that I'm referring to. How might this actually impact you in your homework and quizzes and tests and things? Well, for example, if I have x approaching 0 and tangent of x over x, which is not the same as what's above it, what I can do is realize that I'm going to rewrite tangent of x as sine of x, and then the x is still down there, over cosine of x in the denominator with the x. Then you can take that and rewrite it as a product of two functions, one of them being sine of x over x, and the other one being 1 over cosine x. And since it's a product, we know that we can use one of the properties that we learned earlier to say that this is the limit of the first function times the limit of the second function probably put parentheses around that for clarity. And according to the theorem that we just found out, that the value of that first limit is going to be 1. And then let's try substitution. Cosine of 0 is 1. 1 over 1 is 1. 1 times 1 is, of course, 1. Okay. And if you look at a graph of tangent x over x, as x approaches 0 from both sides, it indeed approaches a y value of 1 as x gets closer and closer to 0. Okay, that ends this lesson, so I will see you in class.